Thank you very much. Good afternoon, everyone. It's an honor and a privilege to speak in this distinguished forum, and I'd like to thank the organizers for making this possible. And so in the spirit of grand challenges to which this meeting is devoted, clearly the maybe grand challenge for DFT is to achieve true predictive power. In other words, to get to a position where we can really, just based on the atoms in the system, do a true first principles calculation and come up with the correct prediction of some experimental behavior or property. Now, the problem is that in the words of Niels Bohr, prediction is difficult, especially about the future. And indeed, most applications of DFT are really interpretative and not predictive. In other words, there is an experimental result, which then DFT helps to explain. Now, there's definitely no shame in adding chemical and or physical insight to an intriguing experimental finding. And yet, the situation can be described a little bit tongue-in-cheek as first the experimentalists discover something interesting, and then we theorists predict it, which is, of course, not the ideal state of affairs. But that's not always the case. So in the next half an hour or so, I'll try to share some stories of prediction, lack of prediction, and what we can do about it. So why do we expect prediction in the first place? So this has already been explained very well by the previous speaker. We expect prediction because if we do calculations, in this case in the ground state, the previous talk was about the excited state, based on the Kohn-Sham equation, then we know that this mapping is in principle exact, in the sense that the density we would get from this mapping to a non-interacting electron gas would yield the same density. It does so with this magical exchange correlation potential, which is the functional derivative of the exchange correlation energy, and everything should work. But again, since we don't know what this exchange correlation potential is in general, then it's in principle exact, but in practice always approximate, and indeed getting better and better approximations for the exchange correlation energy or potential as a functional of the density is in some sense the holy grail of this problem. So that's why we can expect predictive power. But as again already mentioned in practice, we use approximate functionals. There are many functionals out there. Most of them are either based on LDA, the local density approximation, GGA, which is the same but with gradient corrections, and also hybrid functionals, on which I'll have more to say later, that introduce a fraction of exact exchange. And these are, of course, all various levels of approximation. So the real question in a theory that is in principle exact is how are we doing in practice? And that brings me to one of my all-time favorite sayings, probably, and that is that principle and practice are the same in principle but not in practice. So the real question is, what's happening in practice? So let's start with an example where everything works as well as can be expected, which is taken from work that I was involved in already a while ago, but I think it's informative, so I'll show it here. And that's a study of silicon clusters, small silicon cluster anions. You see 4, 5, 6, 7, and also deuterated silicon cluster anions. And for each of them, there is an experimental photoemission spectrum, which was taken by the group of Gerd Gantefohr at Constance University. And then for each of them, we come up with the structure, and then from the structure, we can get a theoretical prediction for the photoemission spectrum, which is actually naturally broadened by molecular dynamics, so there truly are no parameters here except for the atomic number of silicon, and for that matter, hydrogen. And you can see that in all cases, there's quite a good or even excellent agreement between theory and experiment, despite fairly rich spectra in some cases. So of course, that's not really a prediction for the photoemission spectrum because experiment came first here. But this is a prediction for the structures which are not known. And they were found through simulated annealing within DFT, and some of them are not obvious. For example, the silicon 7- is a bipyramidal structure, which means that the top and bottom atoms are 5-fold coordinated, and the coordination number of 5 is not the first thing that typically comes to mind when you think about silicon. But this is the case here. And how do we know that these structures are good in the absence of direct experimental confirmation? because it turns out that the photoemission spectrum in most cases is very sensitive to the structure. So for example, for silicon 6-, this is one structure. There's another structure just a bit higher in energy, which is different, and its photoemission spectrum is completely different. And in one case, you can see that all peaks and even sub-peaks are well predicted, and in the other case, this bears no resemblance to experiment. So it's a fair bet that these structures are indeed correct. And all of this, by the way, was with the simplest functional possible, which is LDA. So this is a good case, but life is not always that easy. Here's another example from work that Oded Hod from Tel Aviv University and I did a few years ago. And we were looking at van der Waals interactions in hexagonal boronitride, which is the inorganic analog of graphite, with basically alternating boron and nitrogen atoms in the same structure. And now we ask, okay, so what's the, if we bring sheets close to one another, either as a bilayer or in a bulk, what's the equilibrium distance between two sheets? And if we do that, say, for the bulk, which is this purple line here, first of all, the intersheet spacing is way too large. I'll show you the correct answer later. But more troubling is the fact that the binding energy is just a measly 2 millielectron volts per atom, which means that this thing shouldn't even hold together at room temperature. And now, if in the example before it was as good as it gets, now it's about as bad as it gets, because, you know, there's not much else to say if the prediction is that a well-known material isn't even supposed to exist at room temperature, right? So we're done. There's nothing else to say. And this is with PBE, which is actually an excellent GGA function. So how did things go so horribly wrong all of a sudden? Well, one issue is that all the approximations that I mentioned a couple of slides ago actually have one thing in common, and that is that they don't know how to treat dispersive interactions. And the reason is because if you think about dispersive interactions, say induced dipole, from the point of view of DFT, this is really a long-range correlation effect, and those functionals simply do not have long-range correlation built into them. Now, in the last decade or so, there was tremendous progress in this area through various physical ideas. I'll just mention one, which is my favorite because we found it to be really useful in our work, and it's also simple. And that is to simply add the leading perturbation theory long-range pairwise interaction. So namely, between each two atoms, add a term that is C6 to the, over R to the power of 6, which is the correct asymptotic form of van der Waals interactions, times some damping function that would prevent this from adding interaction in the long range, in the short run. Now, this seems awfully empirical. This idea has been around for a while, but hey, if I can play with a damping function and I can play with the C6 coefficients, I can get any answer that I want to, so that's hardly making a prediction, right? But the point is that some years ago, Alex Tkachenko and Matthias Scheffler came up with a recipe to actually determine these C6 coefficients from first principles based on scaling of the density. I won't take you through the details. You're welcome to ask me later if you'd like. And then all of a sudden, this really is a true first principles result, and actually Alex and I have worked extensively on applying this to various systems and to show that this works very well. So let's go back to this boronitride example, and now if we add those dispersive corrections, suddenly, yes, this is definitely going to be stable at room temperature, and the intersheet distance is predicted to be 3.33 angstrom, which is in fact spot on the experimental value. So indeed, that was the ingredient that was missing, and once it was incorporated correctly, predictive power was restored. Here's another much more recent example of the same idea from work that was actually published a couple of months ago. So this is joint work with Leah Dadi and Steve Weiner, who are looking at biological materials. And they were looking at eyes of decapod crustaceans like this prawn here or like this lobster here. They made a very interesting discovery that actually their eyes are based entirely on mirrors. There is an array of mirrors which channels the light over to the retina, which are in in green here. And then there's also a back reflector with fingers. So basically there's a fairly sophisticated optical system based entirely on mirrors, no lens. And furthermore, the material that makes up those mirrors from Raman spectroscopy was identified to be a molecular solid based on this molecule, isoxanthopterin. which before that was not known as a molecular solid at all. And then the question that we were faced with is, okay, it is a molecular solid. We know it's a crystalline solid from X-ray diffraction, but the X-ray diffraction is not of a particularly high quality because these are really nanocrystals. So what's the crystalline structure? So we asked the computer to sort possible structures based on one leading chemical intuition idea, and that is that these planar molecules would probably like to form a network of hydrogen bonds. And eventually we came up with this suggested structure. So if you like, this is nature's idea of a two-dimensional material like graphite or boronitride. It really is, again, in individual planes. And in the plane we have a network, just like before, except that if with boronitride we had a partly covalent, partly ionic network throughout, here it's a hydrogen bonded network, so one can still recognize the individual molecular units. Now, based on this predicted structure, we calculated the hypothetical X-ray diffraction. So if this is indeed the structure, this is what the X-ray diffraction pattern should look like. And then these are patterns that were later obtained from these two fellows here with synchrotron experiments. And as you can see, this prediction really is borne out by experiment. So this really was a prediction in the sense that theory came first, experiment second. And to tell the whole story, actually, we predicted two structures. The other one turns out to be the one that one obtains if one tries to form this crystal synthetically. So there are two polymorphs, and theory was able to identify both, actually. Now, sometimes there are unexpected results also when you try to just interpret data. So this is part of a collaboration with Udi Gazit's group at Tel Aviv University. Udi's group synthesized a few years ago a bio-inspired material based on diphenylalanine, which has this interesting and actually quite beautiful structure. And they found that this has unexpected mechanical stiffness. So they found that in certain directions, the Young modulus, which roughly speaking is like the spring constant for a specific direction of press, is almost 20 gigapascal. And to put this number in perspective, cortical bone is just 13 gigapascal. So something that you'd think would be soft and squishy actually is stronger than bone. So how come? So we calculated it. Our theoretical prediction was also high, but only about 10 gigapascal. Still, we felt that this was enough for at least a qualitative interpretation, and we came up with a model that explains this in terms of those sets of interlocking rings, which we call the zipper effect. I won't go into the details of this, but I would say that in terms of prediction, we made a few speculations in the paper about where the remaining difference could be coming from. One of them was that possibly there's a role of water. So if water can get trapped in the spore here, then this should assist the mechanical properties. And indeed, later work, not by us, showed that in theory, if you add water in the pore, indeed, the Young modulus jumps to 20 gigapascal. And if you take these materials, and experimentally, if you take these materials and desiccate them better, indeed, the Young modulus goes lower. So this is another case where the interplay between theory and experiment really lets you understand, even quantitatively, where remaining differences were coming from. And also, based on this, we were able to make really a prediction again. My student, Ido Azuri, who was doing this work, said, well, if van der Waals interactions can cause such stiffness, then what about hydrogen bonds, which are even stronger? And so he took glycine, which is the simplest amino acid, and looked at the glycine solid, and calculated and found that indeed one would have very high Young moduli, as high as even 40 or 50 gigapascal, so more like a soft metal already. And it would be also highly anisotropic, so it would depend on the direction from which you press this, precisely because it depends on the orientation with respect to the hydrogen bond network. So we went to Meir Lahav, who's a well-known expert in these types of materials, and to his credit, he was very skeptic, but was willing to entertain us. And so finally this was measured with nano-indentation experiments, and indeed it's highly anisotropic and very high. So this is indeed another case of prediction. So now let's change topics and up the ante a little bit. So far I was only talking about things that in principle should have worked, in practice may or may not have worked, and with better functionals we can get them to work better. But now let's talk about something that DFT even in, or Kohn-Sham DFT even in its exact form is not supposed to do. And one such property is the relation between the Kohn-Sham gap and the fundamental gap. The fundamental gap is defined as the difference between the ionization potential and the electron affinity. So the difference between the minimum energy of taking out an electron and the maximum energy gained from putting one in. Ideally, one would like to equate the HOMO-LUMO gap of the Kohn-Sham single electron levels with this. This would make life easier. But already a long time ago, Perdue and Levy, and independently Shem and Schluter, showed that this is not so because of a peculiar property that the exact Kohn-Sham potential has, and that is known as the derivative discontinuity. It's a uniform jump in the potential as one goes across an integer number of electrons. And the reason that this happens is because, you know, it's not a physical potential. It can have various singularities, and this is one of them. So when you try to extract an electron, you approach this limit of an integer number of electrons from below. When you add an electron, you approach it from above. So you miss this constant, and so Kohn-Sham eigenvalues don't mimic the quasi-particle picture even in principle. So again, what happens in practice? So here's one example, free-base tetraphenylporphyrin. Nothing magical about this molecule except for good reference data. So here's the experimental ionization potential electron affinity, and here's the optical gap, so minimum energy for an optical excitation, which is much smaller owing to strong electron-hole attraction in this molecule. This is many-body perturbation theory that Hardy mentioned in the previous talk, and it's doing quite well, which is to be expected, but it's more expensive. If we do GGA or B3-LIP, the time-dependent DFT actually predicts the optical gap very well, in agreement with the conclusions of the previous talk. But if you took the highest occupied and lowest unoccupied eigenvalues seriously, you'd be in deep trouble because they're off by 1 volt to 1.5 volts, and the gap is too small by 3 to 4 electron volts, which is absolutely unacceptable. So if something is not supposed to work in principle, and indeed does not work in practice, then it would seem to be a fool's mission to do anything about it. But there's wiggle room. And the wiggle room is that we don't have to stick to Kohn-Sham theory. We can talk about generalized Kohn-Sham theory, which was first phrased in this paper by Zeidel, Gerling, and co-workers, Mel Levy, in 1996. And the idea there is that instead of mapping to a non-interacting electron gas, as Kohn and Sham did originally, we can map to a partially interacting electron gas as long as it's still represented by a single Slater determinant. Then through some math that I'm suppressing owing to time constraints, the bottom line is that one gets this equation, which again we have the ionic potential, but now we have the capability for more complex operators, and in particular a non-multiplicative potential as in Hartree-Fock theory, as in the Fock exchange operator of Hartree-Fock theory. But unlike Hartree-Fock theory, now it's exact because there would always be a remainder multiplicative potential that would make this exact again. So from this point of view, even Hartree-Fock theory becomes just as another fairly crude but special case of DFT. Now, because we have a non-multiplicative operator now and we're still doing rigorous work, there's the hope that we can mitigate this derivative discontinuity problem by burying some of it inside the non-local operator. I already showed you that doesn't work for a simple hybrid functional, but it can work for a more sophisticated class of hybrid functionals, which is known as range-separated hybrid functionals. The idea there is that we partition the 1 over r Coulomb repulsion between electrons into a long-range term and a short-range term, for example, with the help of an error function. So, as written, it's a trivial identity that error function plus the complementary error function is 1. But now the point is that in the long range, we will treat this the Hartree-Fock way so that we will get the correct asymptotic potential. And in the short range, we will treat it the GGA way so that we get a good balance between exchange and correlation. And if we do that, then the only remaining issue really is how to choose this parameter gamma. In other words, what's short range and what's long range. So the answer in some previous literature, such as these articles, was, okay, let's take some data set and figure out some compromise number. So again, that's empirical, so it runs contrary to the spirit of prediction. It also turns out not to be sufficient for spectroscopy. So what we did instead, and this is, as was already mentioned, joint work with Roy Baer and Tamar Stein, who was then a student working with both of us and recently hired as faculty at the Hebrew University, was to instead rely on a physical requirement, and that is to insist that the ionization potential theorem, which is an exact theorem within DFT, be obeyed. In other words, this theorem tells us that if we did have the exact magical functional, the highest occupied eigenvalue really would be the same as the total energy difference between the neutral and the cation. Now, there's no such theorem for the electron affinity owing to this derivative discontinuity business, but one can insist on the same for the ionization potential of the anion. One then has two demands with only one parameter, so one can minimize this and say the least squares sentence. Now, the point I really couldn't emphasize enough is that when you do that, you do have a parameter that may change from system to system, but by no means is this parameter fit to anything. It's not fit to experiment. It's not fit to some other theory. It's obtained by demanding on an inherent or an intrinsic self-consistency requirement. So it is predictive. Prediction is not lost. How does that proceed in practice? So here's our pet molecule again. Here's this condition for the neutral species. If it's obeyed, the sum of the eigenvalue and the ionization potential from total energy differences is 0. Here it is as a function of gamma. There is a point where it drops to 0. Here's the other condition, same for the anion. That's the green curve. Here's the average. And we have a winner. Now we're going to freeze this winner, never touch it again for this molecule, do DFT, do TD-DFT, and we're in business. Now we can actually restore the excitonic picture that before existed only in many-body perturbation theory and restore predictive meaning to the highest occupied and the lowest unoccupied states. So at this point you could say, well, that's maybe nice, hopefully nice, but that's one molecule. So how general is this? So in collaboration with Jeff Neaton's group at UC Berkeley, we were looking at this for the so-called G2 set, which is a set of 148 small to medium molecules, which were actually used to train the B3-LIP functional at the time. So this is epsilon homo coming from the calculation. This is the experimental ionization energy. And as you can see, our results hug the straight line. If experiment and theory agree precisely, everything is on the straight line. And B3-LIP consistently underestimates it. Now, you could argue that, again, this is not really predictive because the experimental ionization energies are known and were, in fact, taken from the NIST dataset. What this doesn't show, though, and I think it's a nice story, is that in the original version of this plot, there were 10 blue crosses here that were huge outliers by a few eV. And the students involved in this, Ivan Rafaeli Abramson and Isaac Tamblin, saw no particular common denominator between the 10 cases that didn't work. There was neither a chemical nor a physical common denominator, so they decided to dig deeper, and they went back to the NIST data book from where this was taken and to the original experimental literature, and discovered that there were 10 mistakes in the data set. About 5 of them were just typos, and the other were reliance on old data that was not accurate enough and has been revised since with new experiments. So we actually sent an email to the curators of that data set, and they corrected the data, and this is already compared to the new data. So I think this, when I thought about this later, I realized that this really is predictive power in the sense that Isaac and Sivan were effectively arrogant enough to say that if there's disagreement between theory and experiment, then something must be wrong with the experiment. So that, I think, is a case of prediction. Of course, I don't advocate for this arrogance in general. Could lead into a lot of trouble. Okay, let's talk briefly about the charge transfer case, which was also already mentioned by Hardy. So that's another case where standard functionals run into trouble, and this is most easily seen by thinking indeed about the limit of a well-separated donor and acceptor, which was actually already treated by Molekin in the early 50s. And Molekin said, well, the minimum charge transfer energy is really easy to calculate in such a case. It's just the ionization potential of the donor, which is the energy I have to pay to liberate the electron from the donor. Then I'll get the electron affinity of the acceptor back when I deposit the electron on the acceptor. And then there's also a 1 over r energy, which is the attraction between the electron that is now there and the hole that I left behind here. And so I gain that as well. Now, if I compare this to linear response DFT, then this should be HOMO minus LUMO. If it's a hybrid functional, then also minus a fraction of 1 over R. So I just showed you that in a conventional functional, epsilon HOMO is not the ionization potential, epsilon LUMO is not the electron affinity, and the fraction of Fock exchange is not 1. So in other words, you can understand why it won't work, because the first term is wrong, the second term is wrong, the third term is wrong, but other than that, everything's fine. Right? But with this optimally tuned range-separated hybrid, I hope to have already convinced you that the ionization potential is the highest occupied eigenvalue, the electron affinity is the lowest unoccupied one, and 1 over R we get for free by virtue of having the correct asymptotic potential. So this should work, and indeed it does work. So here's comparison to gas phase experiments from Hanazaki in Japan, where the donors are simple aromatic molecules, benzene, toluene, etc., and the acceptor is tetracyanoethylene. So these are the experimental numbers. Here's what you get with time-dependent GGA. You see that there's a really large underestimate by more than 2 electron volts, so it's a very strong quantitative error that makes this qualitatively useless, because you're sending the experimentalist to the wrong spectral regime. Using B3LIP doesn't really improve things all that much. Using a range-separated hybrid, but with a fixed range separation parameter that is taken from thermochemistry, does cause some improvement, but not enough. Now it's overestimated. And if you use our optimal tuning agreement, now you're in business. So there's some comparison here to many-body perturbation theory that I'll skip. Instead, I'll show you a recent result from last year, not from our group, from Thomas Bredov at Bonn University. They were studying this really large charge transfer complex, where it turns out that the lowest charge transfer excitation energy is from the macrocycle to these edge groups. And there's also a valence excitation at almost exactly the same energy, which is why there's only one experimental line here. And then they tested a variety of DFT and many-body perturbation theory methods, and you see that they're all over the place. So most of them are no good. There are only 2 methods here that are actually close to experiment. One is many-body perturbation theory with reiteration of the Green's function. So not even simple many-body perturbation theory. And the other is the optimally tuned range-separated hybrid approach. So that gives you another idea that really one can make predictions here. Now, I want to say one word about the formal underpinnings of all of this procedure. Of course, the Kohn-Sham equation has been suggested and proven by, not surprisingly, Kohn and Sham back in 1965. The extension to time-dependent DFT had to wait a while and was actually done by the previous speaker. That's the famous Runge-Gross theorem from 1984. I already told you that generalized Kohn-Sham theory was suggested by Seidel et al. In 96. But recently, Roy Baer and I realized that nobody actually covered this corner. In other words, can you prove time-dependent DFT also in the generalized case? This hasn't been done, even though everybody, including ourselves, have been using that for many years. So we decided to do that, and we did do that, and it's actually going to come out in a special issue in honor of the previous speaker. But I would like to really say, in all honesty, that this red new paper here is not at the same level of significance as the other 3, because all these 3 required a radically new idea, and that's hard. This just required the synthesis of existing ideas. It's maybe not trivial, but it's a lot easier. So this should be said frankly. Okay, one last thing, maybe 2 or 3 slides and then I'm done. One last thing I want to talk about is gap renormalization in molecular solids. So an interesting phenomenon is that if we go from the individual molecule to the crystal, even if the molecules are very weakly interacting, the gap will shrink considerably. The HOMO will be pushed up, the LUMO will be pushed down, and the gap will be much smaller. Why is that? It's basically a dielectric response effect. If you try to take an electron or give an electron on one molecule, then the rest of the molecules polarize. You have a dielectric image charge. Image charges were already mentioned today. And so you have a polarization energy, which basically reduces the ionization potential and increases the electron affinity. That's another phenomenon which is well captured by many-body perturbation theory, as you can see in the red lines here. Again, joint work with Jeff Neaton's group. So benzene, pentacene, C60, all of them show a very large renormalization. But DFT with almost any function, with any functional really, is blind as a bat to this. So again, a failure. It's not predictive. It doesn't predict the renormalization. Why not? Because again, the electric response is a highly non-local correlation effect, and those functionals can't see it. Actually, our range-separated hybrid also doesn't see it, but one can simply add it in by insisting that the asymptotic potential now, instead of being 1 over r, as we go to the solid state, will change to 1 over epsilon r, where epsilon is the dielectric constant, which can be computed separately. So if we do that, then actually, yes, then for, I believe, the first time, we can actually get DFT to follow this renormalization effect as well. So we can also add this as a predictive tool. And one very last slide is that the same idea can now be taken from molecular solids also to non-molecular solids. So if we think about lithium fluoride, for example, if we change this range separation parameter so as to agree with the known gap, and then compute the band structure, we get band structure that's in excellent agreement with GW. But what's even more important is the optical absorption. We chose lithium fluoride because it's notorious. If you do lithium fluoride with something like time-dependent LDA or GGA, you get this curve here. Experiment, on the other hand, has this sharp excitonic peak. In other words, again, it's a non-prediction. There's no relation between theory and experiment. Many-body perturbation theory in red here gets it right. And with our new screened range-separated hybrid, we get it right too. And this is from a consistent framework. In other words, the exchange correlation, energy, potential, and kernel really are all coming from the same source, so one is the derivative of the other. So let me just quickly summarize. Clearly, there are many questions that are still open. There are many difficulties that remain, and the road is still long. Nevertheless, at least in some cases where the conventional point of view is that DFT or TD-DFT cannot quantitatively predict issues like molecular gaps, charge transfer excitation energies, photoemission spectra, renormalization molecular solids, or band structure and excitonic line shapes in solids, which are the various examples that I showed you. Sometimes we can take the knot out of there and restore predictive power after all. And with this, I'll stop. Thank you very much. I'll be happy to take questions.
We have time for one question. Yes, please.
About the very last slide that you showed. So the excitonic spectrum here in lithium fluoride. As you know, many of the strong insulators have a series of peaks, essentially the hydrogen series. Can the range-separated hybrid that is targeted here for solids, can this be captured by that functional?
So we're only now starting to look at it in detail. So the short answer is we don't know yet, but we have good reason to believe that the answer could be yes. Again, because the asymptotic potential is correct, and because we know that the unscreened version of this functional really does capture the Rydberg series in something like the hydrogen atom and other atoms, because it provides the correct asymptotic potential, which standard GGA or hybrid functionals does not. So I'm optimistic. Needs to be proven. We're working on it.
Thank you.
Well, thank you very much.